Hi there. This is a video describing graphical analysis of the concept speed and velocity using either a distance or position graph. So this is the set of objectives we're working on. In this video, I'm going to assume that you've already done a little bit with speed and velocity, but again, we're going to focus on the graphical aspect of those concepts. Here is a reminder of the definition. Speed is a rate of change in distance. It's a scalar. Velocity is rate of change in position, which is a vector, it has a direction aspect. Here are some formulas that you hopefully have already seen and used, and they're based on the definitions. Average velocity would be delta d over delta t, change in distance per time. Average velocity would be delta r over delta t, change in position per unit time. In physics, we're often interested in whether or not a quantity is constant. So does an object have a constant speed? Does an object have a constant velocity? Here are some comments on that idea. And those are special cases. They're going to show up nicely in graphs. So we won't dwell on this right here, but you can pause the video and look over this if you haven't considered this before. So in the video here, I've got a couple of example graphs, and we're going to analyze the graphs to determine speed and or velocity. So one type of graph that we often use in physics is a distance versus time graph, like we see here. Distance versus time shows how far an object has moved. The length of the path traveled is the definition, versus time. So if we kept track of how far an object has moved, as time goes on, we can produce a graph like this using data. If we look at this graph, we'll notice that we have a slanted or sloped line. At least the second part of this graph looks like a sloped line. Well, we could find the slope. And slope is very important when it comes to analyzing graphs. So the slope on any graph is always delta y over delta x, and you know that from math. However, on this graph, if you think about what is on the y-axis, distance, and what is on the x-axis, time, the slope on this graph will be delta d over delta t, change in distance divided by change in time. And that would be speed on this graph. So this is a very important idea in physics, that if we're looking at this graph, the slope of the graph represents the speed and is equal to the speed of the object for which this graph, for which the data on this graph is valid. So we're going to do some examples in the PowerPoint here. We'll show some examples of finding numerical values. So hopefully you remember how to find the slope between 2 points. So if I pick 2 points on the graph, at 5 seconds, t equals 5 seconds, the distance traveled was 90 meters. At 8 seconds, the distance traveled was 120 meters. I can calculate the slope, delta y over delta x. So 120 minus 90, that would be 30 meters, divided by 8 minus 5, that would be 3 seconds. That's 30 meters divided by 3 seconds. That's 10 meters per second. And what that's telling me is that on this graph, that part of the graph shows a speed of 10 meters per second. A linear graph would indicate a constant speed. There's only one slope here. You could pick any 2 points on the line. If it's a linear graph, there's only one slope. And if we see a linear piece of a graph like this, then we say, hey, the object had a constant speed on that part of the graph. So that's an important idea. Let me also point out a couple of things here. We're finding the slope using the units on the graph. 2 squares over on this graph happens to be 1 second in time. 1 square up is 10 meters, so the slope is 10 meters rise over 1 second run. However, we're not just looking at the blocks. If we were just looking at blocks, we would say the rise is 1, the run is 2, the slope would be 1/2. But you can tell that it's a steady up and over, up 1 over 2, but on this graph, that's equivalent to 10 meters per second. So that is an example of using the slope to find speed. The first part of the graph, however, appears to be a curve. So what do we do if we're interested in the speed where we have not a line, but a curve? Suppose we want to find the speed at 2 seconds. So I put a little red dot here at time equals 2 seconds. Notice that at that particular point in time, the distance is 50 meters. 50 meters divided by 2 seconds would be 25 meters per second. But that's not the speed because that's not the slope. So what we do in a situation like this is we use the idea of a tangent line. So I'm going to show a red line coming in here. And this red line is touching the curve at one point. And in math, we know that's called a tangent line. That tangent line has a particular slope. And we can find the slope of that line. So we could pick any 2 points on that line. These are not actually points that apply to the object. These are just 2 points. I'm mathematically finding the slope of that red line. And once again, I can do rise over run, delta y over delta x, and this time that would be 20 meters per second. Notice that's not 25 meters per second. This is the slope of the curve at the instant in time where the line touches the curve. And what that means is that at that instant, the instantaneous speed of our object has this value, 20 meters per second. How does that make sense? Well, if we think about what's going on here, where the red line touches the blue curve, well, they're equally sloped on the graph. We can imagine even a little piece of the blue curve would be more or less linear. And that would be the same slope as this red line that we've drawn. So using this tangent line allows us to find the slope of a curve. And that's a way to determine and really kind of define this idea of an instantaneous speed. This is what it would look like on a graph. So we could say, okay, at the instant where it touches at 2 seconds, the instantaneous speed of our object was 20 meters per second. Now, if we look at the graph as a whole, we can see that there's a linear part and a curved part. So here's a straight line, this red line, and using that line, I can tell, right about here, at time equals 4 seconds, that's where we get a transition from a curve to a straight line. And then that allows me to interpret this graph and say the following. Okay, until I got to 4 seconds, I had a changing slope. Here I showed a tangent line anywhere along that region. And where that's occurring, the slope is actually getting less. And that would indicate a decreasing speed. So the first part of this graph shows an object that's slowing down. And speed was decreasing because the slope of the graph was decreasing. But then after that, it appears to have a constant speed because that part of the graph appears to be linear. So this is an example illustration, just an arbitrary example, but showing a few important ideas about analyzing this type of graph, distance versus time. A different graph that we can analyze and often like to use in physics would be a position graph. So here's a position versus time graph. And this one might strike you as odd if you've never seen such a thing before. So notice over here the units, position, meters, comma, in. Well, position is a vector, and that means it has a direction associated with it. And in is the direction, north. We can graph a vector quantity for certain situations. It's kind of a funny thing to do, but if we're just specifying how far north an object is from some point of reference, we can keep track of that. Well, how far north is it at any point in time, at 5 seconds or 7.5 seconds or whatever, and then create a graph. And then that would be position versus time. I have an animation or two to help you think about this graph since you might not have seen one like this before. So first of all, we can just imagine, okay, the position is decreasing up until a certain point, and then the position increases again. All along, the position apparently is some number of meters north of something. Now, let's suppose that we imagine an overhead view of a person. Suppose this is a graph illustrating the motion of a person, say on a football field. And the person is starting out at the 50-meter mark on the football field. Well, usually in yards, but almost the same thing. Anyway, a person is out in the middle of a football field, and they have a certain position, which I've shown as a vector r. And we're imagining an overhead view of this person. But then the person starts moving. And as they move, that position vector shrinks because they're getting less north than they used to be, and then they turn around and go back the other way. So I hope that what you just saw makes sense to you. You could rewind the video and watch it again if you like. But that's what we're trying to show with this graph, is that, okay, here's the position of this person in the form of a vector, how many meters north, and how it changed as time went on, as that person was moving. After we get that straight in our head, well, then we could do basically the same thing we did on the distance graph. We could say, hey, look, here's a linear part of this graph, and hey, I could find the slope. And the slope on any graph is always the same thing, delta y over delta x. The slope on this particular graph, though, is change in position per change in time. So how much the position has changed per unit time, well, that's the rate of change in the position, and that's velocity. On this graph, the slope would be equivalent to the velocity of our object. So we're going to find some numerical values for our moving person. We're imagining it to be. The first part of the graph is linear, so once again I could find a slope. And you probably remember this. Hey, that's a slanting down line. It's going to have a negative slope. The change in position is a negative quantity, and that makes the slope a negative quantity. And then if I get this value, what is that telling me? Well, negative 5 meters per second means that the position vector was decreasing by 5 meters per second. And since I was measuring how far north, if my northward position is decreasing, it's because I'm moving south. So the negative sign on that slope basically means opposite of north. And that's an important idea. So over here we had position north. When we get this negative sign right here, that's telling us, oh, this is a velocity that is south. Now for my answer here, notice I did not say negative 5, positive 5. Normally we give a vector quantity with a positive magnitude and then some indicator of direction. So the negative sign basically turns into a direction. And then we have something similar to what we said previously. Oh, well, hey, if I have a linear graph, there's only one slope. I could pick any 2 points, and anywhere along that line, the velocity should be the same. So that would be the velocity of the person at 1 second. That would be the velocity of the person at 3 seconds. That would be the velocity of the person at 2.5 seconds, and so on. Anywhere along this linear piece where the slope is the same, apparently our person had a constant velocity. Here I have an example of using a tangent line. So the second part of the graph appears to be curved, and once again we can use the idea of a tangent line, and we could find the slope of a tangent line. And if I find this value, I get 7.1 meters per second, which would be a positive slope. And then what would we interpret that to mean? Well, this time, if we get a positive slope, that means in the same direction as our label over here, north. So that would give us the velocity 7.1 meters per second north. And at what point in time? Well, the point where the tangent line touches. And that point is at 8 seconds on this graph, which has half-second increments. So if you look at the graph, you look at the scale down here, here's 7.5 seconds, and then one more increment over, that's at the 8-second mark. That would be the velocity at that instant our person was moving northward at a rate of 7.1 meters per second. Now here's an interesting point on the graph, the lowest point on this graph. If we drew a tangent line there, we would end up with a horizontal line. Hopefully you remember this from mathematics. If you find the slope of a horizontal line, what do we get? 0. Slope is 0. What does that tell us? That tells us the velocity would be 0 at that instant, which is about 6.3 seconds on the graph. Now, if you watch the animation of the person, that would be the instant where they turned around. Well, okay, yeah, you would have to stop moving south before you can move north. So there has to be an instant in there where the velocity is 0, and that would be the low point on the graph, where the slope of the tangent line is 0. That would be an instantaneous velocity of 0 at that particular point in time. And then we could look at the big picture here, kind of like before. That point on the graph kind of breaks the graph into two parts. There's the part with a negative slope, and all along that, our person is moving southward. And then there's the part after 6.3 seconds, and that would be all positive slope. That would indicate our person moving northward. And again, we saw that in our little animation. I hope that that's making sense to you. If we have this graph, we can find the velocity at any point. We can determine whether it's constant or not, and we can determine the direction of the motion. That would be true for linear motion. If you had an object moving in 2 dimensions, you would have a more complicated situation. You would need 2 of these graphs, but for the time being, we'll be focusing on linear motion, and then we can get lots of great information from this graph. I hope this video has helped you understand how to use slope to analyze either a distance or a position graph and determine speed or velocity, and whether or not those quantities are constant.